In this video, we will talk about problem G from Codeforces round 928. You are given some rooms and the edges represent the wall between the rooms. Now, you need to make some of the walls thick so that music does not flow into a vertex that is labeled as S. You need to minimize the number of thick walls that you need to have. Notice that making a wall thick is equivalent to deleting that edge from the tree. Now, the problem can be rephrased as, given a tree, break it into the minimal number of connected components such that music and silence do not exist in the same connected component. Why is this statement true? Because if this and this were in the same connected component, then it means that there is a path between them. If there is a path between them, then music from this vertex can flow into the silence vertex, which we do not want. So you can notice that the resulting tree would contain some connected components. In fact, it will only contain connected components of three different types, which we will talk about later. But before we do that, let us do a color coding of all the vertices. So if a vertex has music in it, we'll color it with green. And if a vertex has silence in it, that is music is prohibited, we'll color code it with red. So just like a traffic signal, green would imply that music is allowed and present. Red would imply that music is prohibited and also absent from that vertex. And white means that that particular vertex does not have a preference. Let us talk about all the connected components that would remain at the end of the operations. If a connected component contains a green vertex, it is obvious that it cannot contain a red vertex in this connected components. Similarly, if it contains a red vertex, it cannot contain a green vertex in this connected component. Therefore, the connected components can only be of three types, either containing white plus green vertices, or white plus red vertices, or only white vertices. Not only that, you can notice an interesting property of the connected components. That is, if this connected components has at least one green vertex, then the music from this vertex will flow into every vertex of the connected components. So this is the homogeneous property of the connected components. That is, if this vertex has music, it will flow to every connected element. Similarly, if this vertex prohibits music, then all the vertices in this connected components should prohibit music. Similarly, here none of the vertices have a preference, so all of the connected component would remain white. Therefore, a connected component can either be colored all green or all red or all white. Now let us root the tree at vertex 0. Can you tell me the color of the connected component in which vertex 0 should eventually land in? If you think about it, this is not an easy question to answer, because if the initial color of vertex 0 was white, it could either land in a connected component that is green or in a connected component that is red. A greedy strategy might not work in this case. Therefore, it is safer to incorporate all the possibility via some DP. We do not know the final color of the connected component, but one thing that we do know is it has to be either green or red or white. So this prompts us to a DP definition wherein dp of u comma c is the cost to fix the subtree that is rooted at node u, and the color of the node u's connected component is going to be color C. Of course, in the final configuration, we do not know the best color for this node. So it is optimal to choose whatever is the best option available out of the three color. So we can take the minimum of them. Since we have defined a DP for this particular node, and these children, right, they are also subtrees that are rooted at some particular node, we can compute the DP value recursively for all of these children. All that remains is to figure out a strategy to compute the DP value of the node U once you have all the DP value of the children. But this again is a very difficult problem to answer, because if in your mind you start thinking of all the children at once, it becomes too overwhelming if you try to apply some combinatorics on all of the children, right? So let's simplify the problem for you. What if I told you that every node will have just two children? Can you now fill the DP value of this node given the DP, all the DP values of this and this node? This is of course an easier task from this one, but still a difficult one nonetheless, right? So let me simplify the problem a bit more for you, right? What if the tree contains two children per node, and for this particular node I already attached this children for you. I update the DP value of this node when only one children is present, and now you need to add another child and its subtree that follow to this particular node and update its DP value. Can you do that? This question is now a bit easier to answer, and we will soon see a strategy on how we can do that. Suppose that this is node U and I have attached the subtree of the first child for you. Your job is to attach the subtree of the incoming child to this node and then populate this new DP values of node 1 into this NDP array. Also, recall from the homogeneous properties of a connected component that all the nodes in a connected component would be of a single color, right? So that is why on the left hand side you see that the existing connected components created till now, they all have color green, and the incoming subtree have color white. Now when you try to merge these two connected components, you have two options with you. You can either decide to keep this edge or you can delete this edge. Let's talk about the case when you delete this edge from the tree. So if you delete this edge from the tree, someone still has to account for the cost that is needed to fix the subtree rooted at this node, plus the cost for deleting this edge. So that is why NDP 1 of green would be 1 for deleting this edge, plus DP 1 comma green for fixing its own subtree with the left child, plus DP of 5 white, right? Because it can be fixed independently. Now what about the case when you keep this edge? So if you keep this edge, then it would simply be the cost for fixing this subtree and the cost for fixing this subtree. Now what happens when you combine these two connected components? Using the homogeneous properties of the connected components, you can see that all the green color would flow to this connected component as well. Therefore the resulting connected component would have color green. So that is why if you keep this edge, you will have to update the DP value of green. Now you might think that okay, this value and this value are same, right? And definitely we want to minimize this NDP1 comma green, right? So why not always keep this edge in this situation, right? Because it is always beneficial to keep this edge, because you can allow this color to flow into this connected component. That is true, but the point is that with DP, you do not need to think about each and every possible scenarios, right? Of course, you can think of each of these details, but this will also work, right? Like first you try to keep the edge, then you try to delete the edge, and then you use some mathematics to compute the minimum, right? Why do you want to expend your own energy in figuring out what's the optimal strategy, right? Since we are anyway exploring all the possibilities with DP, we should have the correct answer with us. Now, once you have the strategy of merging a children into the existing tree, you can see that it is not necessary for the tree to contain only two children, right? As then when children keep on coming in, you can just keep on merging children with the same logic. Why? Because once these children are merged, all of them would become a single connected component with just one single color, and then your previous merging logic would also work. So all we need to do is figure out a strategy to combine this left half and this incoming children in all possible scenarios. There are a total of 3 into 3, that is 9 different combinations that can occur during a merge. Of course, in all of these combinations, if you decide to delete the edge leading to the child, then the resulting connected component would still have the same color. Therefore, you need to update the NDP of that same color. But let's talk about the case when you decide to keep the edge leading to the incoming child's subtree, and whether or not that is allowed. So when you merge red with red, the resulting subtree would be red. So you update the NDP of red for this particular node. When you merge red with green, this merge is illegal because this connected component prohibits music and this connected component has music, right? So this merge should not be allowed, and therefore you have to necessarily delete this edge. Then when you merge red with white, the resulting connected component will have color red because all the color will flow down over here. So you will update this NDP of this node. Similarly, this merge is not allowed. When you merge green with green, you need to update the NDP of green. Then when you merge green with white, you need to update the NDP of green because the color will flow down over here. Similarly, when you merge white with red, this color will flow up and into all of these nodes. Therefore, you need to update the NDP of red for this particular node. Same thing when you do a merge for white with green. And when you merge white with white, all the connected components would remain white, and you need to update this NDP of this. Then once you have created this NDP array by considering all the possibility, you can simply swap out the NDP array with the DP of U array, because you can now add room for a new child to enter by doing that same merging process again. Therefore, we have a very simple algorithm to solve this problem. That is, iterate over all of these vertices that are present in the tree rooted at node 0. Then recursively compute the answer for each of the child. Then start adding the children one by one using this merging strategy. And the merging strategy is very simple. If the parent or the child is white, then the resulting connected component will have the color that is different from white, that is the alternate color. And if they are not, if at least one of them is not white, then the merge is only legal if they are of the same color. And then once you merge them, you keep on storing these values in an NDP array, and then finally you swap out that NDP array with your DP of U. Now, why exactly that swapping and why exactly an additional array is needed? To understand that and to gain more context on that, you can visit my blog that I've written. I'll link that in the comments as well to get more intuition on that. For the code, we simply implement what we discussed so far. Initially, when the root has no children, the color of the resulting connected component of the root would be equal to the current color. So if the root has color green, we set dp u comma green to 0, indicating that 0 cost is required to turn this into a connected component with color green. And of course, to turn it into some other connected component without external help is impossible. So that is why we set all other values to infinity. Same for red and same for white. Then we start the process of incrementally adding the children's subtree one by one. First we run DFS on the child to populate the DP values of the child recursively. Then we try out all the 9 combinations of the parent and child combination, right? Because even though this is one child, it can exist in 3 different forms. And even though this is one node U, it can also exist in 3 different forms, R, G and W. Then we iterate over all of these 9 possibilities, and notice that in all of these 9 possibilities, we are always allowed to delete that edge by paying a cost of 1. If you delete that edge, then the resulting answer for that node would be the cost to fix that subtrees node alone without the incoming children plus the cost of the incoming children. Then when we decide to keep the edge leading to the incoming children, we need to figure out the resulting color of the connected component. As we discussed earlier, if one of the parent or child is white, then the resulting connected component would have the color equal to the color of the other entity. But if none of them is white, then the merging can happen only when both of them are equal. If they are not equal, then the merging is illegal. And once you have figured out the color of the next connected component, you simply update the DP value of that by saying that the color, the cost to fix the parent is this and the cost to fix the child is this, and we do not need to spend any time or spend any money to attach the parent and child. So you update it in NDP array, and finally once you have processed this children, you swap out the NDP array with the original DP array so that you can make room for a new incoming children's subtree. The time complexity of this entire algorithm is O of n, because for each child, even though there are 2 nested for loops, the overall complexity is O of 1, because this loop only runs 3 into 3, that is 9 times. The technique of incrementally adding children to a node in tree DP problems is very powerful, and it can help you solve a wide variety of problems. However, you need to be mindful of problems in which there is an easier solution using the combinatorial approach if you just think about all of the available children at once. But when this approach starts getting complicated or overwhelming for you, then you can switch to this approach. That is, instead of thinking everything at once, think about what happens when you merge 2 different state of the parent and the incoming child. So to help you get more familiar with these concepts, I have created 2 blogs which utilize the same trick of incrementally adding children. So those blogs are called DP on induced subgraphs and DP on spanning subgraphs. And these blogs also have 11 practice problems in total. that you can submit on my Codeforces group to verify whether you have really understood these concepts or not. All of the code that is discussed in this video and the ones that are discussed in these blogs, they will be available on cfstep.com, but I will also link the entry point in the comment section on YouTube.